Okay, for the first part, I just need to give a bit of self-introduction about me. All right. After that, we'll just jump straight into the WA2 revision. So first of all, thank you everyone for joining me on this Monday night. It will be a very productive 2 hours. A bit of intro about myself. I mainly teach chemistry and physics. I've been teaching for quite a while. So every year I take about 80 to 90 students per batch. My students nowadays keep telling me that I'm growing older, which is kind of true. Okay, but for me, I do find it very enjoyable. Fun fact, I only teach Sec 4s because I love the desperation. Sec 3, sometimes people still very relaxed. But Sec 4 is like, O level is coming. Yeah, I thrive on that kind of anxiety. But more about myself, on top of just teaching, I also have hobbies. I'm just a human as well. So I played floorball since secondary school days. I still currently play a little bit. But as you can imagine, I find it hard to run very fast on the court. So struggling a little, taking it more recreational now. Fun fact, I used to play for the national team, but that was just for one competition. That was my highlight. After that, cannot take it already, all right? On top of that, nowadays, in my free time, I do like to play Mobile Legends. Those of you into K-pop, I'm probably before you because my era was when there was Ice One, and now the different members are all in the different groups. So I feel like a very proud father watching over them, if that doesn't sound creepy. Okay, I'm also pretty into NBA and stuff, all right? But enough about me, because later on, as we go through, we will learn more physics now, okay? But this is just a bit more about myself. I need to clear up the rest of the slides, so just bear with me. So for those of you who are new, never heard of OVERMUGGED, we are a team of tutors specializing at O level and A levels. Right now, most of you are currently at the Kovan unit. We also have 2 other branches at Bukit Timah as well as Marine Parade. And this year, we'll be expanding to more branches across the board. I think what we're quite excited about is to see so many students excited to join us and to let us be sort of like the helping hand as we traverse across O levels and A levels. So last year, we pretty much got onto a lot of news and stuff because we are one of the first few centers to do large-scale mock exams. To give you a bit of a teaser, we'll be doing it again this year at much larger scale for both our students and external students that are interested to apply. So imagine you get to sit for a full prelim paper before you sit for your prelim, or to sit for a full O-level paper before your O-level paper. So definitely in terms of your time management, exam strategies is going to help a lot. So keep a lookout if you're interested to join. So currently, these are our branches. Our Kovan branch is pretty new. Right here, this place has only been up since January. So you guys are sitting in one of the newer centers. Upstairs are our classrooms as well. So both upstairs and downstairs. Now, most of the time, people will be interested to ask, hey, you say your students are 60 to 70% get A, real or not? Real, I can show you all the spreadsheet, but a bit lazy. Really, most of my students, almost none get lower than a D3. But the reason is not because of like some secret juice I make them drink before the exam. No, the chicken essence doesn't really help. But it's really the consistent hard work that you put in. The very fact that you're here for WA2 revision, physically or online, tells me something like that you care about your results. And that is honestly the first step. So most of our students are pretty motivated to do well. And I think being motivated to do well is the first step, but putting yourself through the right training program matters as well. So my style is we grind pretty hard. So my students will know every week there's homework, but it gets you to the end point. All right. Next, learning resources. Today you have received the handout. Later on, I'll also be giving out free periodic tables for those that want. Okay, but at the end of the lesson. Welfare, by the way, those that are here, please collect. Please take the snacks if you want. So I know a lot of your first time Paisi, right? Like, oh shit, I need to be like Singaporean. I'll be like very quiet. No, you can go and take the snacks. Okay, it's free flow. Nobody's gonna stop you. Whatever lah. Okay, can, sure, yeah. Question, yeah. Yeah, let's start. Okay, so everybody, let's flip over to the handout. All right, so over here we'll be starting with current electricity. Midway through, I might take a pause when we reach DC circuits. Then in the second half of the lesson, we're going to go through practical electricity. And if I have time, only if I have time, then we'll do magnetism. Why? Because magnetism is very easy. Okay, don't look at me like, watch, I need very intensive revision. No, the bulk of it will be DC circuits. All right, but without getting it right, without getting current electricity right, DC circuits is going to be more difficult. All right. So overall here on the handout, whenever I do annotations, if you find it to be useful, please copy alongside me. All right. We start off with the foundational stuff. These are things I expect you to know already. Starting with the word current. Okay. Definition of current is rate of flow of electricity. You might be like, okay, sure, I get it. So one thing that I want you to take note of is that in your working, you will never write current equals to charge over time. What you do is you always write I equals to Q over T. So it might be helpful to write this down in case you're not familiar with the symbol. A PDF can be downloaded on the Google Drive posted on Telegram. Okay, now, whenever we encounter the word current, whenever we encounter the word voltage, these are words that you're familiar with. But most of the time, what I experience with Sec 4 students is that when you learn this chapter, what do you learn? You learn the formulas, but you don't really understand what's going on behind the current. So with my own students, what I like to do is what I call a visualization exercise. So I'm going to make this real quick. We're going to cover it in 2 minutes, but I'm going to show you guys how to think about electricity. After that, the chapter will get a little bit easier to understand. All right, so I'm going to go through this very fast because honestly, not much time. But over here, what I've done is I'm going to show you a visualization of a circuit. Now, I know most of you don't play Pokemon anymore, but it's my childhood lah. So I'm going to use Pokemon as an example. Now, the battery is where the energy is at, right? So the battery is the source of the energy. Now, let me ask you a very simple question here. So what is the energy store here? From what to what in the battery? It starts off as chemical potential, right? What does it turn into or transfer to? Electric, right? So over here, right, how I need you to visualize the process is that in your circuit, there are what we call charges. What is a charge? A charge is simply a particle responsible for transporting this electricity around the circuit. Another analogy that I always use is imagine a GrabFood driver, right? So what happens at the restaurant? The GrabFood driver picks up the food. The food in this case is electrical energy, all right? And they will deliver this energy to the house. In this case, they will deliver it to the light bulb. So what exactly is a charge? A charge is just a unit that transports the electricity around the circuit. You can think of it as a car, a GrabFood driver, or in my case, Pikachu is the one carrying the electricity and bringing it around the circuit. As it brings it through the circuit, it delivers it to the light bulb. This is when the electrical turns into light and heat. Now, once they finish the delivery, the Pikachu no longer has any energy left. But this charge would then go back to the battery to get refilled again. It's like an F1 car on a circuit. As it goes out, it's full tank. But as you drive through the circuit, you use up the oil. By the time you go back to the pit stop, you have empty tank. They'll fill you up with oil again to go for another round. So in short, what are certain words that are loosely thrown out? Number one, charge. What is a charge? It's simply something that carries electricity around the circuit. If charges are flowing through the circuit, we can associate it with the word current. Current is the rate of flow of electricity. So take note of the definition now. Rate of flow of electricity. If you have 3 charges passing through the circuit per second, that is 3 ampere. 10 charges, right? Because a lot of GrabFood drivers going out at the same time during dinner period. 10 ampere. So how many charges per second? That is literally current. So what's the difference? Previously, you could say, teacher, I memorized the formula already. Right? It's just I equals to Q over T. But with a little bit of understanding, the chapter can be slowly unlocked. So I just want you to think in your head, imagine the charge moving across the circuit, delivering the electricity, going back to the battery. How many of them are flowing per second? That is current. So you have 5 charges per second going through the circuit, that is 5 ampere. So in that sense, yes, you need to know the formula, but you need to be able to visualize electricity as well. Now, the one that is traditionally more difficult is voltage. Now, take note, voltage is a unit. Most of the time when you want to use the term accurately, highlight for me the word electromotive force and the word potential difference. Voltage is a unit. So in case you cannot tell the difference, unit is basically current's unit is ampere, right? But current is current. So don't use the 2 words interchangeably. Now, to make it as straightforward for you as possible, what is the difference between EMF and potential difference? EMF is always referring to the battery. The one providing the energy, the source, EMF. Electromotive force is your pit stop for the F1 race. It's the restaurant in which is giving out the food for the GrabFood driver to go around. Then what is potential difference? Potential difference is always used for the components. In this case, the component here is the light bulb. So you will say EMF of the battery, potential difference of the light bulb. Now, what is potential difference? It is basically before and after 3 volt before. After I pass through, I use up all my voltage, right? After that is 0 volt. So what is the difference before and after? That is 3 volt. So potential difference. Now, imagine this. Currently, my circuit only has 1 light bulb. Okay? What if I decide to add in a second light bulb? There's also 3 volt. What do you think would be my new EMF? Anybody? Typical Singaporean. Your EMF will be 6 volt. Why? Because if you need to pass through the first light bulb, you're going to use up 3 volt. You pass through the second light bulb, you use up the next 3 volt. So in a scenario where you have 2 light bulbs, 3 volt, your EMF has to be 6 volt. The battery is going to give you just enough to complete 1 round around the circuit. The more obstacles you're going to put along the way, more components, the battery has no choice but to give you more energy to start with. So what's the relationship between EMF and potential difference? If you add up all of your potential difference, that's your EMF. Because EMF is a supply side. How much do I need to give you to begin? Depends on how many components you have. The more components you have, the more EMF you need. Take a hand out first. Okay, so what words have we covered so far? We covered the word charge. We talked about current. We talked about voltage. All right, so voltage is meant to be used up as we go along the whole journey. I don't think I have questions, so I'm just going to move on. All right, we go back to the handout. So the 2 formulas that we are looking at is current as well as voltage. Now, I want you to be very careful with the way the formula works. Take note, voltage is work done over charge or energy over charge. If you write this out, things might be a bit clearer. What is 3 volt? 3 volt meaning there's 3 joules per charge. So 1 charge, when I first leave the battery, I'm just alone. How much energy do I possess? I possess 3 joules of electrical energy. That is 3 volt. So when I say 3 volt is the light bulb, what does it mean? It means that when I pass through the light bulb, 3 joules of energy from electrical to light and heat. So the term voltage here is very simple. It's per charge, how much energy are we talking about? If I leave my battery with 6 joules of energy, I'm 6 volt. So for each charge, how many joules of energy do you have? Think back to the GrabFood driver. In his pack, right, how many energy did he store inside? If in his GrabFood bag, there's 6 joules of energy, we call him a 6 volt. Because he's delivering 6 joules of energy per charge. Okay, if that starts to make a little bit more sense, electricity would progressively get easier. So we don't just memorize formula. We need to be able to visualize what is taking place in electricity. Okay? Normally, I take 20 minutes to explain this. This is a truncated version. But I hope you are following well. But more importantly, I want to apply this to questions later on. The questions are a bit more important. Now, after current, after voltage, naturally comes resistance. Now, resistance, the correct definition is the ratio of potential difference to the current flowing through it. In short, R, as you can see here, equals to V over I. I'm very confident that most of you that have learned this chapter already know the formula V equals to Ri. I don't think that's something that I need to reteach you, but more importantly, how can we apply it to different scenarios later on? Okay, so I won't stay too long here at resistance. I'll move on to cover the next part, resistance of a wire. So resistance of a wire is found by taking L over A. So take note, this row here stands for resistivity. If you have different color highlighter, you might just want to follow me to highlight this properly so that you're able to see, hey, which represents which. I'm going to give you a very important tip later on. So this is length. Okay, and lastly, we also have cross-sectional area. For those of you here that take pure physics, I'm going to emphasize, most of the time, they will not give you area as part of the question. Most of the time, you'll be required to do it this way. R equals to rho L over pi R squared. They would double the diameter. They will half the diameter. Later, we'll see why it's important to account for pi R squared instead. the change is going to be squared. Okay, the question comes, you know what I mean. Okay, but this is very important. If you take note of this, you will not make the mistake in the exam. All right, lastly, Ohm's law. Now, Ohm's law can feel very intimidating because most of you have no idea what's going on. But to simplify Ohm's law, what we can do, right, is to just draw out a couple of graphs for this to make sense. So, ohmic conductor, all you need to draw for me is an IV graph with a straight line. If it's a straight line, we say that this increases proportionally. Resistance is constant. In the real world, there are very few ohmic conductors. The only one you probably need to know are fixed resistors. Those are considered ohmic. Majority, even like filament lamp, is considered non-ohmic. So what is non-ohmic? Non-ohmic translates to resistance will change. I don't need you to memorize this, but I want you to recognize when you see non-ohmic conductors, you plot out the same IV, but the graphs will be curved. Which way it curves, not super important. But you know that the moment a graph curves, we are discussing a non-ohmic conductor, where the resistance is going to be changing. Like I said, later on as we tackle questions, this will get a bit clearer. So straight line, ohmic, because the resistance is constant, right? It doesn't change. But if you get a curve, resistance will be changing. That's why you get a curve. Okay, I'm not spending very long because I want to go to the questions. Now, to be more time efficient, for every single question, I'm going to give you about 30 seconds to a minute to look at the question, try. Half the time, you cannot solve it in Taiwan, but it's okay, right? Because I'll go through immediately. So let's spend the next 1 minute or so just to take a look at question 1, and then we're going to try it together. Do me a favor here, try to map up to what concept or which formula you think you'll need to use. That will always be your opening step. Okay, those online, I wish and I hope you all can participate as well. So feel free to let me know once you all know the answer, type it in the chat. Okay, of course, I'll be going through the full question. So per question, I'll give you about 1 minute lah. Okay. Okay, let's take a look. I had no point asking you lah, because you also we already who answer A, who answer B, C, who thinks D. It's not bad, you all got participate. Okay, can maybe I can ask you. Not bad, not too bad, not too bad. Okay, answer is D. But if you chosen a different answer and you got it wrong, it's fine. But I really need you to learn from the mistake. So earlier, right, you remember what I mentioned here? So over here, right, I mentioned that, hey, this is area. But remember, we will not be using area most of the time. We will instead be using pi r squared. Now, what's the difference? How does this impact you getting to the correct answer? So let's write down the formula first, one more time. Your resistance is found by taking resistivity times length over pi r squared, which is area. If you take a look at your correct answer, which is D, let's see what's the impact of increasing the length and increasing the diameter. So for D, how does it look? For D, R equals to rho bracket 16L. Because our length increased by 16 times. So it becomes 16L over pi. If I increase my diameter to 2 times the original diameter, what happens here is that I'm increasing my radius by twice as well. Bracket 2r close bracket squared. Is diameter the same thing as area? It is not, right? So if you're going to double your diameter, you double your radius. What happens to your area? it actually increases by a factor of 4 times. One more time, you double your diameter, you technically double your radius. Double your radius, your area increases by 4 times because of bracket 2r close bracket square. So mathematically speaking, if I factorize out rho L over pi r square, what I have here in terms of the number is 16 over 4. 16, 2 square is 4. So if we look at it, what's my final answer? Is 4r. Because rho L over pi r square is r. So what am I saying? There's only one thing you need to take away from this question. If this appears in my WA, I will not be so stupid to just assume diameter is the same thing as area. You just need to put in pi r squared. See how much your radius changed, bracket it, square. This one came out in both O-level. It comes out a lot in prelim. I can confidently say this is commonly tested. If your school is nice, they will just change the area. If your school is nasty, they will write diameter. So please pay attention to this particular question, okay? Because if you do not know, straight away wrong already. But I hope after today, you can get it right. Okay, even down the line in prelim and O-level. Let's move on to question 2. Got questions, just raise hand. If not, I'll just keep going. Okay, so go ahead to try question 2. Those online, if you have questions, feel free to check with me as well. All right. But like I said, I answer as many questions as I can. So this one, which concept is being tested? Quite obvious, right? Ohmic, non-ohmic. But how do we approach this question? Ooh, I see people in the chat. For the previous question, the fastest way to get the answer is as per what I've done. So I always show you all the most efficient answer. Okay, anyway, answer for question 2 is B. Now, for some of you are wondering, got this shape, man. Just now you just tell me straight line, you tell me curve. What is this? So let's use question 2 to clearly identify what Q is. Anybody knows? What's the name? Starts with a D. Very good. It's a diode. All right, so use this question to remind yourself, this is how the graph of a diode should look. Now, what exactly is a diode? Very simple. It's a traffic marshal. It only allows current to go in a single direction. So how it looks in a form of a circuit is that it looks like that with a triangle with a dash within a circle. So if you have your diode this way, it will only allow current to flow in the same direction as where the triangle is pointing towards. If you come in from the other side, can you see there is this line here? It's like it's stopping you. So you cannot come in from the opposite direction. You can only go with the flow in the same direction as the diode. I know there are probably very few bio kids here, but if you take bio, it's like your valve, right? It only allows blood to flow in one direction. If you don't take bio, like, what you're talking about, it's fine. Okay, only allows current to flow in a single direction. Now, right now, you might be thinking, okay, sure, I get it. It flows in one direction, but for what? Right? Doesn't current only flow in one direction? If you learn a little bit further, you'll learn that there's this thing called alternating current. Alternating current means the direction of the current can change. So how do I change from alternating to a single direction? The diode will come in. So right now, don't worry. You only need to think about it once you reach the chapter, electromagnetic induction. Okay, so it's further down the line in Sec 4, but it will be useful. Now, here the thing is B is the answer, and it's somewhat quite obvious. But what I like to address is actually more C and D. I'm going to teach you all a very simple way to solve this. Okay, so listen up. Let's use R for example. R, I want you to pay attention to the y-axis and the x-axis here. It's current against voltage. The truth is, current against voltage is not the easiest to analyze. So if you're just starting out, I will always recommend redrawing this graph to be voltage against current. Now, you need to be able to visualize when you switch your axis, how your graph is going to change. For those of you who cannot visualize, this is the new shape of your graph. Because from here to here, this is current voltage. You need to flip it to V against I. Over here, what I need you to recognize is that if we draw out the tangent, what can we observe about the gradient here? It's getting steeper and steeper. When we talk about the word gradient, gradient is your y-axis over your x-axis. So I like to call this y over x. But at the same time, if you're going to put V over I, what does it give us? V over I is resistance. So what are we trying to get at here? If you use a V against I, you can actually use the gradient to analyze how your resistance is changing. So in this, here we draw. I need to redraw. Okay, anyway, I do a fast one, so I don't explain again. So the curve goes like that, V against I. So gradient equals to y over x, V over I equals to R. So what I'm saying is that if you take a look at your tangent, we can see that the gradient of the graph is increasing. So what does that mean about resistance? It is increasing up. So in short, what do you do if you ever encounter a non-ohmic conductor? How do you analyze how the resistance is changing? My recommendation, change it to a V against I first. Because when you do that, your gradient is your resistance. By looking at how the gradient is changing, you can then see how your resistance is changing. So conclusion, the resistance of R, is it increasing or decreasing? It's increasing, right? So this statement is wrong. Question. Can, but that's provided you are smart. Okay, let me elaborate on that point. It's true. So over here, right, you're like, sure, why do I need to redraw the graph name? Why not, right? I just say gradient equals to, in this case, I over V. And I'm smart enough to say that I over V is 1 over R. Which means that in this case, if we notice how the gradient, can you see, is decreasing, what's happening to the resistance? Because it is inversely proportional. Resistance here is increasing. You will come to the same conclusion. But because my style is that you're technically not my regular student, I do not know what standard you're at, right? To be honest. So for me, I'll teach what I think is the easiest to understand. But that is a faster way. Why? Because you don't have to redraw the graph. So both methods will work. I'm going to throw in one more bigger statement. If you ever need to explain this, you cannot use the gradient to explain. It's a bit confusing. Let me clarify. 1 minute, okay? Gradient is not y over x. Gradient is dy over dx. So if you're verbally answering a structured question, you need to answer it based on the ratio of v over I, not the gradient of your v against I curve. I read one time. If it's a written explanation answer, don't use the gradient. Gradient appears straight away wrong. You just need to say the ratio of v over I is increasing or the ratio of v over I is decreasing. Then you can justify how your resistance is changing. Okay, but when you're analyzing, gradient is fast-free. It's very easy. In your head, it works. You get the answer. In MCQ, can already. Okay, but when you write down written answers, don't write gradient. Clear? Okay, moving on. Worksheets can be downloaded from the Google Drive. This one, I'll just give you 30 seconds. This one, if you know, you know. If you do not know, then you do not know. Answer? Quite easy, right? I see some people online. Answer is D. Now, if you understood what I was saying in the previous question, this question is easy. Why? The graph is already V against I. So what did I just say? I said that gradient, you can technically look at it as y over x, V over I, technically gives me resistance. As we look at how the gradient is changing, the tangent that I'm drawing is getting steeper and steeper. Gradient increase is my acknowledgement that my resistance is increasing. Clear? Does not obey Ohm's law, meaning I expect you to know that we are looking for a curve. Which curve? Depends. So you better not choose A lah. A is ohmic, right? B, C, D are non-ohmic. But which one matches a scenario where resistance is increasing? It should be D. So in other words, if you made a mistake here, I need you to be very careful and take a look at your X and Y axis. Just now when I drew out earlier in the notes, right, my axis was actually I against V. That's why this curve represents increasing resistance. In short, pay attention to your axis. It will change, right? Sometimes VI, sometimes IV, right? A different axis creates a different analysis. So please be very careful about this. All right, let's move on. This one, 30 seconds. This one you cannot solve, I'm gonna fail. You don't want it, please don't take out a calculator here. There's no need for a calculator. Come, what's the answer? What's the answer? Confident, it's just D. What's the formula to use here? I equals to Q over T. I is current. This is the symbol for current. Q is the symbol for charge. Time is time. Small t and big T got difference? Can I write like that? What is the big T representing? Period, correct? Right? So down here, we don't use period, we use time. So do I even need to write out the working? 50 charge over 10 seconds, like 5.0 ampere. Can I? Moving on. Okay, another variation for Ohm's law. Let's see if you guys can get it right. This one, I'm going to give you all 1 minute. All right. Wow, some of you so fast. Do until question 5 already. Very good. You read the news. What's the big news in Singapore today? We have our 4th Prime Minister coming soon. Yes. I was reading Reddit and it was like, but you all don't know, you all know Naruto? Never mind. It says like the 4th Hokage coming. But anyway, never mind, ignore me. 30 more seconds, then let's go through the question. You all recognize, right? This is the same thing again. It's the same as question 3, question 4, question 5. Why? Your school, right, will not test question 4 one. Not like, wow, current you got to charge over time. That one you don't need to come WA revision, you also know. The graphs will be the one that we have. So you get the graph right, you get your pi r square right. Actually, current is okay. DC circuits is where the torture begins. Okay, the part that I expect all of you all to know is that if this is a straight line, you almost certainly can tell me that resistance is constant. I don't think anybody's going to struggle with this analysis. The analysis that is more difficult is traditionally the second part here where it's a curve. Once again, pay attention to what is your y and what's your x-axis. So over here, right, let's go with the faster method that was recommended earlier. Over here, my gradient is found by taking y over x. I over v is 1 over r. How is my gradient changing? It's getting gentler and gentler. My gradient is decreasing. Therefore, my resistance should be increasing. This is the faster method, right, that we talked about earlier. If you struggle, what can you do? You always have the option to redraw this portion to be V against I. It will be straight followed by curving this way. You can still make the same analysis now that your resistance is increasing. Because for the graph that I've just drawn, your gradient here is resistance. So you need to ask yourself, which one am I more comfortable with? Am I going to be the style that will redraw it? Or am I just going to analyze it by taking it as 1 over r? Both are fine, as long as you get the correct answer. My style for my own students, I always tell them, you learn both. so that when you check, you can use a second method to double check if your understanding is correct. Okay, but once again, make sure when you explain, you talk about the ratio, not the gradient. Okay, if not, here's the fun part. Let's move on to the structured questions. Okay, for the structured questions, unfortunately, I will not have the luxury of time to slowly explain to you bit by bit or give you time to try. So instead, what we're going to do is you're just going to have enough time to read the question. Then we're going to do it together. Okay, that will be a bit more time efficient. Okay, so I'll trouble everybody just to read the question and then we'll analyze it together. Ready? Yeah, I hope you have enough time to read it through. Okay, so now, as we take a look at this question, I think it's very important for us to understand, right? In order to fully understand what's going on in the circuit, you really have to identify the path of the current. That is very important. You need to know how the current is flowing through the circuit. Otherwise, you cannot solve the question. Now, the situation here states that the switch is open. Obviously, if it's open, we cannot pass through it. Current always flows out from the positive terminal of the battery. So it flows out from here. Sorry, I use yellow color. Because electricity is yellow. No, I'm just joking, okay? You cannot see electricity. So if it doesn't pass through the switch, what that happens, it will pass through L2. It will pass through the variable resistor and ultimately come back home, passing through L1 back to the negative terminal. So earlier we said, right, a charge is delivering electricity around the circuit. It begins a journey by leaving the battery, going through L2, going through R, going through L1 before returning back home. The resistance of the variable resistor is gradually reduced. So we say that the resistance here is decreasing. Now, what happens to the brightness of both lamps? So it's very important here to bring in the formula V equals to IR. Why? Because as we all understand, if your total circuit's resistance drops because your resistor is gradually reduced to a minimum, what happens to your current? Your current will increase. Low resistance, high current. No? And the current is larger, what happens? They become gradually brighter. Feel free to start on your corrections, all right? So what is the brightness of both bulbs? They will initially have the same brightness. The reason why they will have the same brightness is because they are both part of the same series circuit with the same current. Right? Earlier when I highlighted, the whole thing is the same color, it's just yellow throughout. The entire thing has the same current. Same current means same brightness. And as we explained, as resistance drop, the total resistance of your whole circuit decreases. Current increases, your bulb gets brighter. So if you take a look at the mark allocation, this question is broken up into two parts. One mark for stating what happens to the brightness. A second mark to explain how did the brightness, like why did it change? So the stating part, you must first start off by saying same brightness, then become brighter. That's one mark. Second mark you get is when you say because resistance drop, current increase. That's your explain. So for every single question, you need to pay attention to the way the question is phrased. So state and explain. If they just say state, you don't need to explain. No. That means you just say, oh, become brighter, can already. That's your mark. You don't need to talk about the formula, what current resistance though. But the moment explain appears, you need to talk about the formula, how it affects one another. Okay, I'm very appreciative that all of you are copying down, doing corrections and whatsoever. But in the interest of time, you have the answer key also. So if I move on already, you don't like, hey, no lah. You can take a photo too, all right? But you can always refer back to the answer key. We did provide the full solutions, right? So don't be too worried on that. Now, the one that I think is a lot more interesting is now switch S is closed. With the variable resistor with its minimum setting, what is the potential difference across XY? We go back up to the question to take a look. So imagine right now, we close the switch. So instead of an open circuit here, the switch is closed. Does the current still flow in this same original path? I see a lot of you are shaking your head. Fantastic. But why not? I close the switch only, the current should still flow. Okay, this is one word I like to bring up. I always call it path of least resistance. It's like human being, you always take the easiest way out, right? Same for current. So I want us to explore the new path for current right now. If you take a look over here, the starting part is still the same. But as I reach Y, now I'm at a crossroad. Do I pass through L2 or do I pass through S? L2 is a bulb with resistance. S is just a piece of wire with no resistance. So which path would I prefer to take? Obviously, the path of no resistance. So how would the new current flow? All of it will flow through S. None of it will flow through L2. In other words, what happens to the brightness of lamp 2? No brightness, because there's literally no current flowing through it. So if you take a look at the answer key now, what is the potential difference across XY? It will be 0. Right? Because I passed through the wire without the light bulb. Without the light bulb, there's no potential difference. So potential difference is 0. You might be wondering, sure, then what happens to the brightness of L1? If you go back up to the question here, last time there used to be L2. There was resistance of L2 that was accounted for. With this new pathway that the current is flowing, L2 is no longer part of the circuit. What happens to my total resistance? Is going to drop. Current is going to increase. L1 is going to get brighter. All right, so if you cannot follow, you might just want to type this out. Now, current no longer flows through L2. Right? Total resistance decreases. Current increases. Brightness of L1 increases. Okay, because the question here simply asks us to state, we don't have to explain. But if you require the explanation, you can also copy down what I've typed up for you guys. Okay, another 20 seconds, then let's move on to question 7. Question 7, to be fair to you guys, you kind of need a little bit of DC circuits already. Okay, but it's a very simple question, so let's use this as a warm-up question for DC circuits. I'm assuming all of your schools have already taught DC circuits. If you haven't, it's a bit worrisome. Should have lah. Most of you will have lah. Right, so you all should be able to try question 7 as well. Okay, we have a question here. Why doesn't the current split into 2 paths? Very simple. It's because one of the paths literally has no resistance. So if it's a path of no resistance, all of the current will flow through it. None of it will flow through the light bulb. But if both the paths have light bulb, then the current will split. So it's a very logical decision by the current. One path, no resistance. One path got resistance. All of it will take the path of no resistance. Okay, potential difference across XY is 0 because there's no component across XY. Because the current no longer flows through L2. Okay, I hope I managed to address those questions. Otherwise, we'll move on to take a look at question 7 over here. I'm going to do you guys a favor, and I'm going to instantly redraw this circuit for you. I hate it when the 4 is here and the 2 is here. Why make life so difficult? Why not? Why not? just draw this as a single 6 ohm. You get it? Because 2 and 4, but I'm in series. So I might as well just merge these two together and look at this as a 6 ohm. Because the moment you're able to do that, calculating the effective resistance is so simple. The formula in DC circuits that you all should be familiar with is 1 over R equals to 1 over R1 plus 1 over R2 plus 1 over R3. It's just your 3, 2, and 6. This will give you the resistance of the parallel component. Let's not forget there's one more resistor here in series. You just need to add in that 5. Your effective resistance is 6 ohm. So in case you cannot follow, this is in parallel. These 3 are in series. These 3 are in parallel. So when you put the 3, 2, and 6 together, effectively, it's as though it's 1 ohm. Then you just take the 5 plus the 1, that's your total resistance. Not very difficult. This is a warm-up. Give yourself some false confidence until we reach potential divider. Yeah, I quickly move on. So how do you then figure out the current flowing through the 5 ohm resistor? It's really as straightforward as doing I equals to V over R. Okay, how do we know this? It's because when you're looking at the current flowing through the 5 ohm resistor, I need you all to understand that the current here that we're describing flowing through the 5 ohm is your total current. Right? Because all of the current that's flowing out from here is, sorry, my direction wrong. I need to change my arrow direction. My bad. I didn't see the plus and minus carefully. Current flowing through here is your total current. Can see? So imagine the flow of the current. It comes out from the positive. At C, it splits up into lane 1, lane 2, lane 3 in parallel. They recombine back and to the main current from D onwards, pass through B and back to the battery. So what is the current flowing through the 5 ohm resistor? Is the total current. To calculate the total current, you simply take your total voltage, which is 12 volt, over your total resistance. Be a bit smart here, because whatever you solve in part A is usually required for part B. So they will not make you calculate total resistance for fun. So you're like, okay, if I really calculate total resistance in part A, how do I use it to my advantage in part B? Okay, it's by recognizing that total current equals to total voltage over total resistance. Moving on. And what is the potential difference across the 5 ohm resistor? So what you can see over here is that we took 2 times 5. The formula that we have just literally used here is current times resistance. Once again, whatever you calculate in part B is used in part C. So by taking V equals to IR, I know the potential difference across the 5 ohm is 10 volt. What we have seen in the question is that the question did give us that the EMF of the battery is 12 volt. So if you simply subtract the EMF overall minus the potential difference across the 5 ohm, the remaining 2 volt is the potential difference across AB, which is for the parallel components. Every single branch in parallel is 2 volt, 2 volt, 2 volt. Regardless of which lane you choose, going one round around the circuit, you use 10, then 2, and come back with 0. So in total, it's 12 volt. I use 10 volt at a 5 ohm resistor. I'll use 2 volt at one of the branches. You cannot go through all 3, you only go through one of it. But every single branch is the same voltage. So 2 volt, 2 volt, 2 volt. You get what I mean? I just go back up just in case. So if I take a look at the whole circuit, I'll use 10 volt here. Whether I pass through lane 1, lane 2, or lane 3, they are all 2 volt. But as the charge coming through, I can only choose one of the lanes. but every single lane is 2 volt, 2 volt, 2 volt. So when I first pass through this, I'll use up 2 and I'll use up 10 to go back always with 0 volt. So remember, what is the EMF of the battery? It is the amount of energy required for the charge to go one round around the circuit. Yeah, make sure, remember, you don't go through all 3 lanes because you only get to choose one of the 3 paths. So you use 2 volt here, you use 10 volt here. That is how we should be thinking about part C. Okay, and finally for part D, I'm literally just going to remind you all one very simple thing. Minutes, please change it to seconds. Don't tell me how to change to seconds. Okay? Just like 60 seconds, you'll be fine. Otherwise, I'm a believer that we will push on first. We're going to finish up the MCQ component of DC circuits before we take a break. Okay, so we'll go through some content for DC circuits, try the MCQ, then we take a break. After the break, we'll finish up the structured questions for DC circuits and practical electricity. Okay, let's go. Next up, you will see this very important summary page in your notes that contrasts series versus parallel. A few things I need you to know, especially if you have a highlighter, it might be helpful to highlight it in the same color coding that I always do. Over here, I always call it, there's only one river. There's only one path, so no matter what, you have to pass through everything. So current in a series circuit is constant throughout. There's only one river, but it's different in parallel because in parallel, your main river in yellow splits up into 3 individual smaller branches. These 3 branches will eventually combine back to the main river before it returns back to the battery. So what am I telling you? I'm just telling you a very simple fact. In parallel, current will split, but the current will always recombine back before it returns back to the battery. What is the difference? I go back to GrabFood again. Example number 1, the GrabFood driver is delivering food to both the light bulbs. So he will naturally has like more baggage, more food. But in the parallel example, you actually have 3 drivers delivering each food to each battery. Sorry, to each light bulb. So they go to different locations. So current split up. So instead of 1 driver, you have 3 drivers splitting up, each going to 1 light bulb. Okay, so that's how you should be visualizing your current. Now, this is where it gets a little bit more tricky. For potential difference, the EMF of your battery, if it's 6 volt, this means that at each battery, it is 3 volt, 3 volt. As this is a series circuit, for a charge leaving my battery, I need to make sure I have enough voltage to come back home alive. So 6 volt here is because I'll need to use 3 volt at the first light bulb and another 3 volt at the second light bulb. That's all. The one that is more tricky is actually over here. If I say that this is 6 volt, this means that every single branch is going to receive 6 volt. Why? I started with 6. I must return home with 0. Whether I go through lane 1, lane 2, or lane 3, I'm going to be using up that 6 volt. So in other words, this translates to voltage across each parallel branch is the same. Because whether you go to lane 1, lane 2, lane 3, I don't care. You still got to use up the 6 volt. You have to come back home with 0 volt. So later on, as we do calculations, you will need to apply this concept that voltage across each branch is the same. Lastly, for resistance, for series, don't waste time, you just add it up. Okay, for parallel, you need to apply the formula. I think most of you already know this. Instead, we focus on doing questions, all right? That will be a lot more helpful. Okay, potential divider, I won't even teach it because later on, right, when we do the question, I will teach you all through the question. The formula is there. You might need it, but my POV, when I teach my own students, very simple. You understand it first. Okay, after that, you then go back to the formula. So I want to start off with question 1. Okay, I don't expect you all to do this. I'm going to use this question to teach your potential divider. But read first. Some of you might even know how to do already. But I give you a chance to try first. You see a word here, right? Thermistor, right? What is a thermistor? Thermistor is a device which resistance is going to change when the temperature changes. Here, the question stated, okay, temperature is going to increase. When temperature increases, what happens to the resistance of your thermistor? It drops. Okay, you're supposed to know this. You can find this in your textbook as well, in the curated notes if you have. Doesn't really matter. The fact is you must know that when temperature increases, resistance decreases. So over here, I want to start by writing saying that, oh, my resistance here drops. That is your basic question analysis. Now, I'm going to bring up the word potential divider. Now, I want to be very careful here. Potential divider. Let's rephrase it. How do we divide the potential difference? Potential divider. So, how much voltage, how much potential difference do we need to divide? 6 volt. This 6 volt will be divided between the 3000 ohm fixed resistor and your variable thermistor. Take a look at the formula V equals to IR. I just need you to understand a very simple relationship. V and R are directly proportional. If you're going to experience your resistance dropping, what happens to the voltage it's going to receive? It will drop. How does this translate to the question? This 6 volt is meant to be divided between the 3000 ohm and the thermistor. If my resistance here drop, my voltage that I receive will drop. What does it mean for the 3000 ohm resistor? The voltage it receives is going to increase. It's like your mother got $6. So split it between you and your sibling. Right? If your resistance drop, your voltage drop, you receive less money. Your sibling get more money. So what is potential divider? I'm just splitting this potential difference between the two components. If one receives less, the other one's going to receive more. So in this question, what's the answer? Answer is B. Because when temperature increase, my resistance drop, I'll receive lesser voltage. But it will not reach zero. It will only reach zero if the thermistor has zero resistance. If I change the question to what happens to the potential difference across the fixed resistor, it will increase. So what is potential divider? How do I divide the potential difference between the two? Okay? If not, I got a confession to make. My tummy hurts a little. I need to go toilet. So can you do the question 2, 3, 4, 5 first? Then when I come back, I go through. Sorry, it's real. I mean, I'm going to lie to you. I need to go toilet. Okay? So question, you all can try the remaining MCQ question. Once I'm out, I'll go. Which questions are you at? Can you just show me? 2, 3, 4, 5. So fast. Questions, where are you at? Okay, I think I can continue first since we are getting back into the groove. Let's take a look at question 2 next. Question 2, right? My style, you always see me doing the same thing. In terms of question analysis, we make it a point to study how the current flows. Current flows up from the main circuit here, from the positive terminal of the battery. It splits up into 3 parallel circuits. If you cannot visualize, right, let me add in some arrows for you. This over here is your total current, right? Because everything is still flowing through A2 at this point. The current will split up. If we call this I1, current goes through this one is called I3. This one passing through, we call it I4. There's no I2, by the way. It's I total split up to I1, I3, I4. So I total, your total current, is the sum of the current in each individual branch. Since the question did not give us the resistance, it is simply easier to just assume that each resistor here is R. But I think more importantly, right, I want you to be able to group all of these resistors together to call this 3R. Group these 2 resistors, visualize as though it's 2R. Now, why is it so important to associate with resistance? The simple relationship is that the higher the resistance, the smaller your current. So we're going to study how it works across all the individual branches. Now, the reading in A1, we said that A1 over here is 0.6 ampere. Okay, so I1 is 0.6 ampere. How many resistance are there? 2R. So let's just simplify. We call this 2 ohm, right? Just for the sake of calculation. What is my voltage? If V is equals to IR, my current is 0.6 ampere. My resistance, I consider it to be 2 ohm, so 2R. My voltage, we can calculate it as 12.2 volt. My battery is 12.2 volt. Why? Because how many parallel branches are there? There's 3 of them. But what have we talked about? Every single parallel branch have the same voltage. Whether you're talking about the lane passing through A1, A3, or A4, all of their voltage is 1.2 volt. Now, how is this going to help me with my calculation? For I3, how do I figure out what I3 is? Current is equals to voltage over resistance. My voltage is the same across each branch, 12.2 volt. What's my resistance here? I only have 1. So what is I3? I3 is 12.2 ampere. So this one is 12.2 ampere. A simpler way to do this is that what happened to the resistance? It went from 2 to 1. If I halve my resistance, I double my current. I double it from 0.6 to 1.2. You can do that as well. One more time. If I halve my resistance, I double my current. That's the relationship between I1 and I3. So what is I3? I3 is 1.2 ampere. If we use a similar concept now, what's the relationship between I3 and I4? What happened to the resistance? Resistance times 3, right? What happens to the current? Divide by 3. So this 12.2 ampere divided by 3, this is 0.4 ampere. If you're not very comfortable with divide by 3, you can also calculate I4 by taking 1.2 volt over 3 ohm. Right? Because the resistance, there's 3 of it. So 1.2 divided by 3 will still give you 0.4 ampere. So in other words, as we look across this question, the answer becomes quite obvious, right? A2, is there no option for A2? Sorry, A2 is 0.6 plus 1.2 plus 0.4. I believe that adds up nicely to 2.2. A3 over here, 1.2. A4, 0.4. Answer here should be D. Okay? So the sum of each parallel branch adds up to give you your total current. I hope the yellow and the blue helps you visualize that a bit better. Moving on. This one is hard. It's hard. So if you can get an answer, legit not bad. Okay, I know some of you might still be trying, maybe a 30-second wrap up. Then I go through the questions. Okay, so let's work towards our first break, maybe in 10 minutes. Okay, if I bring all of your attention to the screen, let's ignore the answer first. Okay, if you really want the answer, sure, answer is C. But what's more important for me is understanding the thought process towards getting the answer, right? How you get the answer is more important than the answer itself. Now, when the switch is open, I think it's very clear to all of us, this is pretty much just a series circuit. Correct? So you got L1 to pass through, you got L2 to pass through. You probably can think about how that whole circuit will work. What is more interesting is what happens when you close the switch. When you close the switch, does current still flow through L2? Yes. But now I need you to understand that compared to before, my current will split. So my first question is, do you think L2 will receive more or less current compared to before? Less. Because part of the current is supposed to receive, now split and pass through L3 as well. So the first conclusion for L2 is that if current here, sorry, don't use black. If current and L2 is going to have been split, current here will decrease. If current decrease, your brightness will decrease. That's part one. Okay, so part one, the conclusion is because as current splits, current decreases, L2's brightness will decrease. Now, the one that's a bit more interesting is what happens to L1. How did L1 become brighter? Now, the best and most straightforward answer I can tell you is when you close switch, the circuit now turns to a parallel circuit, or is looking more like a parallel circuit. And when that happens, your total resistance is going to decrease. More current will flow through L1. Now, some of you at this point might be like, okay, but like, really? How do you know? In such scenarios, I always recommend doing what I call assigning a hypothetical value. I always love this exercise because it gives you a very definite answer. So imagine, right, we didn't close the switch. Current flows through L1 and L2. The magic number, in case you're wondering, is 2 ohms. Okay, so you think about it this way, L1, L2, 2 ohm, 2 ohm. What's my total resistance in the initial scenario? My total resistance was 4 ohm. Okay, this is before we close the switch. Now, let's imagine we close the switch. What's my new resistance? A new 2 ohm resistor is activated. It's lagging. Okay, 2 ohm. So what we're going to do is we're going to find the parallel portion first by taking total resistance equals to 1/2 plus 1/2 inverse. So how much is the resistance of this parallel portion? Is 1 ohm. So this 2 ohm and this 2 ohm together effectively is 1 ohm. Let's not forget there's a 2 ohm here. What's my new total resistance? Is the 2 plus 1, because this is the resistance of your parallel. The new total resistance went from 4 to 3. All I'm saying is that when we close the switch, my total resistance is going to drop. If your total resistance is going to drop, the current flowing through L1 will increase, making it brighter. Can follow? Not the easiest, but all I'm saying here is you need to be able to visualize how current works. Parallel was going to split. If I change my resistance, my current might increase, it might decrease. So by including L3 into the picture, we have actually decreased the total resistance, leading to the total current increasing. Okay, so that's all for question 3. Anybody has anything you'd like to check? Online students, anybody with any questions? Can you assume that the resistance per resistor is 1 ohm? You totally can. It's just that if you want to follow my advice, I generally find it easiest to calculate with 2 ohm. If you replace it with 1 ohm, you'll come to the same conclusion, which is that the new total resistance is going to decrease. Okay? How to explain if it's an open-ended question? You just need to bring in how voltage, current, and resistance is related. That's all. Okay, but I always recommend hypothetical value of 2 is the best calculation. Okay, question 4, I'm going to go through it very quickly because what is not true is very simple. It is C. Because both R1 and R2 are identical, meaning if I have voltage, my voltage will split equally. So the potential difference across R1 and R2 should be the same. That's all for question 4. Okay, and lastly for question 5, let's take a look. Now, it's quite common that your school will come up with some funny circuit, but it's not the end of the world. Why? You always have the option to redraw your own circuit. Okay, and honestly, if you follow the pathway of the current, it's simpler than it seems. Because current always flows out from the positive. It splits into 2 branches, one over here, another one like that. It recombines back to form the main circuit. So if I were to redraw this circuit, I will always start off with my positive terminal, 12 volt. Ooh, it's lagging. Ooh. It comes out this way. The first thing it encounters is the 1 ohm resistor. The next thing you see is a dot. If I take lane 1, I will pass through a 3 ohm resistor. Get it? Because from here, dot to dot, 3 ohm, dot to dot. The next dot to dot, the pathway is a little bit lengthier. You pass through the 2 ohm first, followed by passing through the 4 ohm resistor. Then the dot goes back to the negative terminal of the battery. Once again, if the colors help, go ahead. So we are technically looking at a circuit with some stuff in series, but the main thing in parallel. But obviously here you don't waste time, right? Like this one, what do? We combine it as though it is 6 ohm. So how do we solve the question? We solve the question by finding your total resistance first. Your total resistance can be found by taking this 1 ohm plus the resistance of this parallel component. How do we put it? We'll do bracket 1/3 plus 1/6 inverse. Because 1/3 plus 1/6 equals to 1/R. Inverse it to find R. After this, you should be able to calculate and find that the answer is 3 ohm. Okay, which allows you to find your total current to be V over R, 12 volt over 3 ohms. Your total current is 4 ampere. Ding. If you can see it without redrawing, don't need waste time. Just do it. But if you're the kind that I a bit uncertain, I recommend redrawing the circuit. It might take a minute, but it's worth it. Okay, and with that being said, thanks for paying attention till so far. We'll go for our first break. 5-minute break, can? Those that need to go toilet. Those that want to snack up. If you have questions, feel free to approach me or raise your hand and I can come over. Okay, those that are online, feel free to type in the chat as well. We will restart and do the structured questions at 8:55. If you're hardcore, you can get started on the structured questions too. How many of your first time here? Was it hard to find a place? You all walk here or you all take bus here? Oh. Okay, do sign up for the remaining subjects as well. It'll be something similar lah. So if you want to come down to the center, it might be a bit more conducive. But for those of you online, if it's more convenient, feel free to join us online. Answer for question 2 for current electricity is B. Yes.
Voltage across the light bulb decreases. It also means that current, sorry, not current, the brightness will also decrease, right?
Yes.
Okay.
Okay, for those of you who are slowly settling back in, maybe y'all can get started on question 6. It's a pretty long question, but I find it to be a necessary one. Let's give you 5 minutes to try properly. Okay, which means at 9 o'clock, I'm gonna start going through this question. Try. If you're not sure, it's fine. Right, just try first. See how close you are to the answer. So at 9 o'clock sharp, I'll start going through. Keep with your friend, go and discuss with your friend. Right? It's fine to discuss and try to do it. Walk around and see what you are up to. I'm not too sure you can think about it. You need to do calculation. Why not start with your resistance? Your resistance will help you find current. Okay, my online gang, make sure if you have questions, feel free to type it in the chat. I promise to reply if I can. 2 more minutes. Before I forget. Guys, before I forget, I'm required to take photo of you. Can you just look at the camera for 1 minute? Real fast. Get the photo. 3, 2, 1. Okay, done. Okay, go back to your question. Legit, I need to photo. No choice. Okay, 1 more minute. People, it is time. Okay, let's go. Okay, definition wise, I'll keep this quick. Just gonna flash the answer real quick. Just take note, the new way schools like to teach you is to no longer just give the dry definition, but to define in context to the question. So in this scenario, you have to mention the correct number here. You cannot just say work done, but 9 joules of work done. Okay, work done and energy is the same idea. So how much energy is required to drive your charge around the circuit? Now, where it gets more exciting is the calculation. But before we go on to the calculation, I'm going to highlight this once again. Really, just to try to give you the impression that every time we do a question like that, it's always about series parallel. So in this question, I want you to see very clearly what's happening is that your current splits up into 2 parallel branches, recombines back and passes through the ammeter. Over here in the first lane, there's 150 ohm, 150 ohm. In the second scenario, there's a fixed resistor with 1000 ohm and your LDR. Your LDR's resistance is going to vary based on your light. Now, they say no light falls on the LDR. Let's take a look. The question was kind enough to, in fact, just give us the fact directly. The resistance of your LDR is 3500 when there's no light falling on it. So over here, if this is 1000, this is 3500 ohm. The question starts off by asking us for the ammeter reading. Ammeter reading is looking for the current. To find current, you just need to take current total equals to your total voltage over your total resistance. You already have your total voltage, right? Because the EMF of the battery is given to be 9 volt. That's easy. The only thing you need to solve this question is to calculate how much is your total resistance. All right, earlier we mentioned before, 150, 150. Don't think of it that way. In fact, what you want to do is to add these two up to become 300 ohm. Same concept, you add these two up, 4500 ohm. So now what we're looking at is 2 parallel, one with 3300 and the other one with 4500 ohm. So if you take a look at the working here, what we did was that we combined the resistors together. So effectively, right, what we are calculating is 300 ohm, 4500 ohm. How much is the resistance like that, right? So 1 over R plus 1 over R. You find the total resistance and hence get the total current. If you ask me, if this is 3 marks, can you get this? Actually, it's quite fair. It's really not that difficult. It's very doable. Okay, so if you are struggling, build the confidence, right? It's about calculating resistance to find your current. That's all. Now, for those of you who are done, if you're taking a look at the voltmeter reading, I want you to pause here first. Listen to what I have to say for the next minute. After that, we didn't care about the answer. So I'm not going to tell you the answer first. We go back up to the question. I want you to absolutely understand how potential divider works after today. One more time. My voltage is 9 volt. It doesn't matter whether I pass through the first lane or the second lane. Either lane that I pass through, I'm going to end up using 9 volt. So a very simple test here. Imagine I got 9 volt, right? I need to pass through 150 ohm and 150 ohm. How is my 9 volt supposed to be divided here? Very easy, right? The resistance is exactly the same. So what does it mean here? The voltage is going to split equally between these two. This means that the first 150 ohm will use up 4.5 volt. The second one will use up 4.5 volt. When it exits is 0 and comes back to the battery, having 0 voltage. You get it? So what's potential divider? How do I split the voltage according to the resistance? You got more resistance, more voltage. If my resistance is the same, then they receive the same voltage equally. Right? Remember your mother giving out money to both you and your sibling? How do they split it? If both of you are equally resistant, very hard to deal with, your mother's like, okay, I just give you all the same amount. But then if you're like you got a very nice sibling and you're the annoying one, right? You're very high resistance, right? Your parent, okay, I give you a bit more, right? So the understanding here is that the higher your resistance, you get more voltage. Okay, not the best example. Then you go back and then you act difficult. Okay, don't say I say that, but you get the idea of what I'm trying to say. Next up, right, over here, the question is saying that they want to find the voltmeter reading. Okay, so how do we find the voltmeter reading between this 1000 and this 3500? So what I want you to visualize is this 9 volt is going to split between these two. So think about it this way. 9 volt is going to split between the 1000 ohm and the 3500 ohm. If you think of this as a ratio, I would say that you probably can visualize that the ratio is 2:7. Math lah, you don't math me, okay? It's just math, okay? You go and divide lowest, what is it called? Lowest common multiplier. No, not sure wrong. However, I just change it to the simplest ratio, 2:7. So my question is very simple, How am I going to split this between the two? You split it according to the ratio. The number is already perfect. Why? Because 9 volt, right? I need to split in a ratio of 2:7. So how much would this 1000 ohm receive? 2 volt. This one, 7 volt. So what is my voltmeter reading across the LDR? 7 volt. It is simpler than it seems. Do we need a formula? No need, because I'm just splitting my 9 volt between 1000 and 3500. More resistance, more voltage. The word here is ratio. We are dividing according to a ratio. But if you look at this in a more exam-friendly manner, how would you express the working? 3500 is the ratio out of 1000 plus 3000. You get what I'm doing? It's basically 7 over 2 plus 7 times 9 volt. Your final answer is 7 volt still. The one in the fraction is the actual working you're recommended to do in school. But the way you think about potential divider should be about, oh, I got voltage. How do I split it? I split it according to the resistance. If you can understand that, things get a lot easier. To further elaborate, this is because the current flowing through both is the same. So if current is the same, V equals to IR, your V depends on your R. Right? They have that relationship. So V is proportional to R. More resistance, more voltage. Okay, so I show you the answer, key answer, pretty clear cut. Indirectly, what I'm saying is don't memorize the formula. That one useless. You need to know how to apply it. That's a lot more important. Okay, moving on to question 6C. Oh, wait, I have a question from online. Can you use the ratio instead to solve? Answer is by right, cannot. Like, that's real talk. Because your school, there's method mark, there's answer mark. Your method mark, they require you to use the fraction. But what I'm saying here is that if you get the ratio, writing out the fraction is actually damn easy already, right? Because it's just math already. At this point, it's not going to be a problem. But the problem is for those students that try to memorize the formula and blindly apply. That is very dangerous. There's a high chance you apply it wrongly. So I think the understanding comes first, then the working comes later. Okay, so by right, you cannot use the ratio directly. Okay, the main thing here is that you need to understand when light intensity increases, your LDR's resistance decreases. So in the past, right, let me just contrast it for you. In the past, 9 volt, is split 1,000, 3,000. Right. So what do we get? We get 2 vote, 7 vote. Now your new one is still 9 vote split. But because the light intensity increase, now is 1,000 and 1,000. This is your LDR, by the way. So how does it split now? It splits 4.5 vote, 4.5 vote. So what the question is saying is that in the past, I used to receive 7. Now my resistance dropped off. I only receive 4.5. So the potential difference has decreased. I thought Chongqing's WA is today. No way. Oh. So different class, different days. Yours is tomorrow. Thursday. Okay, just nice. Revision in time. Okay, I'll move on in 30 seconds for those working on your corrections. Okay, lastly, not much to explain here. If its ohmic resistance shouldn't change, the LDR so obviously changed its resistance from 3,500 to 1,000, right? So resistance of LDR does not remain constant when external conditions like light intensity changes. Ohmic conductor by right, even if your physical environment, external stuff change, the resistance is not supposed to change. AKA like a fixed resistor, right? If I'm 10 ohm, no matter what, I'm still 10 ohm. Whether temperature increase, light intensity increase or decrease, I'm still 10 ohm. That is called your ohmic conductor. Filament lamp is also a non-ohmic conductor because when temperature increases for filament lamp, the resistance actually increases. So a filament lamp is a non-ohmic conductor. If it's safe to put it this way, right? Almost everything is non-ohmic except for fixed resistor. Okay, let's move on. Next up, we're going to look at question 7. We're going to do question 7. Unfortunately or fortunately, is the last DC circuits question I can afford to go through. After this question, we're going to move on to practical electricity already. Okay, so give yourself some time to try. I apologize if you won't have enough time to try everything fully, but let's give you maybe about 3 to 4 minutes to just read through first. Attempt whatever you can. I promise to go through everything properly. Okay, so maybe we'll start at 9:16 to go through question 7. Okay, let's start. All right. So if you have finished, fantastic. If you haven't, don't be worried. I didn't give you enough time in the first place. But let's all take a look at this question together. So here we see once again a thermistor. If you haven't realized the chapter in DC circuits, whenever it comes to circuits, it's very common to see thermistor and LDR. All right. Now, I think what's important here is not just, okay, can I solve the question? But when I look at the circuit, is it abundantly clear that this is a series that's split into two parallel? Whichever branch you go through, you're still going to use up that 1.5 volt. All right. Now, we start off with the question asking us to describe how resistance changes with temperature. It is pretty clear from the graph that when temperature increase, resistance decrease. If you want to be even more precise, mention how it's decreasing at a decreasing rate. Math will teach you how to explain it. Okay, so I don't have to go into detail here. You all probably understand what I mean. Moving on next. Now, this part, right, is a little bit more tedious, but I want to emphasize on which are the keywords we need to talk about. The first thing here is that we were told that the thermistor is cold. Now, if the thermistor is cold, the first thing you need to mention to me is that there is higher resistance. What does higher resistance translates to? It translates to the current is very little, which means the lamp will not light up. This is technically your first mark. The second mark ought to be awarded when you tell me now the thermistor warms up. Implication is that resistance will drop. Current increases. The lamp will start to get brighter. You realize I always highlight certain keywords to you all because the phrasing of the answer doesn't have to be to a T exactly like what I'm writing down here. Doesn't have to be, but you need to capture the key points. So if you mention every single word in yellow, you captured the key idea already. Because you're telling me how the temperature affects the resistance, how the resistance affects the current, and how the current affects the brightness. Done. Then second scenario now, temperature increase. How does the resistance change? How does the current change? And therefore, how does the brightness change? It's a very logical thing. Depends on how you phrase it, but let me put it this way. For this question, explaining using current is a lot more efficient. If you explain using voltage, you are still correct. If I can go a little bit deeper, V is equals to IR. The truth is that your current increasing leads to your voltage increasing, and that affects the brightness. So you're not wrong. But typically, most schools teach current affecting brightness because the resistance doesn't change. Therefore, yeah. But to put it simply, can. But current is a lot more common. Okay, another 30 seconds, then I'll move on from here. Wow, amazed. None of you are falling asleep. Very good. Intense, right? Too bad, you sign up for this, you came here yourself. Okay, my job is to teach you as much as I can within the 2 hours. Okay, but most importantly, I hope you are learning something, okay? Next, we move on to part C. Now, part C, they are asking us, hey, what's the potential difference across the lamp and the potential difference across the thermistor? Don't be too excited to copy this down. Can we just go back to the question to explore once again? The info that was provided is that we're looking at 0.2 ampere, which is right over here. Okay, what I need you to know, understanding-wise, is that whether I go through top lane or whether I go through bottom lane, I have to use up 1.5 volt, no matter what. We are taking the bottom lane now. We know the current, we know the resistance. V equals to IR easily helps me take 0.2 times 10, 2 volts. Okay, wait, am I missing something? 0.20. 0. Okay? 0. Wow, my math ain't mathing, man. 0.02. Then this is 0.2 volt. Sorry, my bad. Okay, so what I'm really making sure that we are clear about is that 1.5 volt, 0 volt, right? Over here, I'm using 0.2 volt. So how much voltage would my thermistor use? 1.5, I need to use up. I only use 0.2 here. This one will use 1.3 volt. I need you to understand this. There's no way to memorize this. It's not a formula. From the journey in the bottom lane, I'm going to use up 1.5. So if my light bulb is going to use 0.2, my thermistor is going to use 1.3. If you get what I'm saying, and now I go over to the answer makes a lot of sense, right? Because the first step, what's the potential difference across the lamp? And since I know 1.5 is supposed to be used up, then I know that the thermistor is simply 1.5 minus 0.2. There's no need to read the graph. There's no need to do any excess calculation here. If not, moving on. We are told to determine the current in the ammeter. Once again, ignore the answer first. We go back up. This is quite simple. You'll probably get it in 30 seconds. We already know the current at the bottom here is 0.02 ampere. How much is the current passing through the ammeter? Very simple. You take the current passing through lane 1 plus the current in lane 2. How much is the current in lane 1? You already know that the voltage across this is 1.5 volt. You know the resistance. So how do I find I1? I1 can easily be found by taking V over R. With my voltage being 1.5 volt, with my resistance already given, 10 ohm. So your current here is 0.15 ampere. So current in I1 is 0.15 ampere. My current in lane 2 is 0.02 ampere. So when I add these two up, what is my total current? My total current is 0.17 ampere. That's all. So blue plus blue gives me yellow. How does the calculation look? As straightforward as calculating current in lane 1 first, adding up the two current. You can think of this as I1 plus I2. Now, to be fair to you, will there be questions that will be more difficult than this? Yes. But the questions we are doing today, are they considered simple? They are considered normal standard. Like, it's okay. Like, if this appears in your WA, there's no way you can complain about it. Most of you should be able to do it as well. Okay? But if you're struggling with the basics today, you really need to spend some time to brush it up. All the questions selected today are reasonable. Okay? Of course, there are harder ones. The harder ones, we take it down the line. Okay? But for now, I hope this is clear, because I like to spend the last 5 to 10 minutes discussing practical electricity. Okay, so let's go over to practical electricity now to finish up this chapter strong. Now, you might be worried, got one more question I haven't go through. How? Answer key is given, right? So you can go ahead to practice, look through the answer key. Now, for practical electricity, I'd like to highlight, given that you're taking pure physics, I think it's essential that you know all three formulas for power. Now, in case you're wondering, these two really need to know or not? My answer directly to you is yes. But the truth be told is actually not that hard, because P equals to VI. The other formula that you have learned is what? V equals to IR. So honestly, this is nothing more than a simultaneous equation, you see. Because if I say P equals to VI, and I sub in V is IR, you get what I mean, right? It's just I square R. Same thing. I can also say that I equals to V over R. So if P equals to VI, V bracket V over R, P is equals to V squared over R. You can say to memorize this, because after a while you get so used to it, you might as well memorize it. But if you're struggling and you're like, what, I cannot remember, just do a simple subbing in. You know P equals to VI, you know V equals to IR. Sub it in, you'll be fine. Okay, so this is not going to be extremely difficult. The next part is electricity consumption. This one, I think most of us understand that we need to calculate it in kilowatts per hour to calculate the cost. Later, as we look through a question, we'll talk about it again. Now, dangers of electricity. Good news is that they are pretty common sense. Now, we talk about each one by one. Damage insulation means you have a piece of wire. The wire spoiled already. So the wire is jutting out. If you touch that wire, you get electrocuted. So never ever touch an exposed wire. Second, if you plug in too many plugs into a single socket, you'll be drawing too large a current. You need to understand that current leads to a heating effect. And if you draw too large a current, the whole thing is going to overheat. It might catch a fire. Life hack, if you smell something like a rotten fish, plastic is melting. Look around your surrounding first, okay? Lastly, when it's a damp condition, meaning there's moisture, your resistance will drop. So when you get electrocuted, when you have water, very jialat because your resistance is very low. For those of you who play games, right, water type is always weak to electric type because water reduces resistance. Okay, next. 3-pin plug, you need to know how it works, but more importantly, how does it relate to your earth wire acting as a protective mechanism? With the earth wire, assuming the live wire goes crazy, instead of the current flowing through to you as part of the circuit, the current will be redirected through the earth wire instead. So it prevents electric shock as your earth wire provides a path for charges to travel to the ground. You can think about it this way. With the grounding and with the earth wire, you can discharge any electricity. This part is important. So 3-pin plug is more important for you to understand the function of the earth wire. Okay, in the off scenario that your live wire suddenly spoil, it got detached or something, it randomly touches the metal casing. If you go and touch the metal casing, you'll get electrocuted. But with the earth wire around, the current will be redirected to flow through the earth instead. You will be safe. So if you go back and you take a look at which are the devices with 2-pin, which are the devices with 3-pin plug, usually a metal casing, you'll see a 3-pin plug. That means the top one will be made of metal. Okay, so that is when you need a 3-pin plug. Okay, the switch and the fuse are all safety devices. Pay attention, they must always be placed on the live wire. Why? Because you want to make sure that you can break off the high voltage from reaching the component. If you put the fuse on the neutral wire, it's no longer able to isolate the component from high voltage. Which means that even though the light bulb don't light up, because no current passing through, right? You go and touch it, you get electrocuted. Which feels damn stupid. Why? Because your fuse or your switch is on the neutral wire. So when they ask you to identify any errors or anything, usually it's about the fuse and the switch being on the wrong wire. Okay, next, moving on. Let's take a look at question 1. All right, let's very quickly do a few quick calculations here. Okay, so I'm going to show you guys what's the right way to approach this. All right, so the first thing is always to convert all of your watts to kilowatts. So I want you to write this instead. Because the unit of electricity consumption is kilowatts. Now that you have kilowatts, hours, you take kilowatts times hours. That's how you get your unit of electricity consumption, kilowatt per hour. Can you help me calculate? 9 kilowatt. Then after that, what do? You just add it all up. All right, I believe that will give you 334 kilowatt. And you multiply by the cost. And I'm pretty sure you get your answer. Okay, so kilowatt per hour question, just pay attention to the unit conversion, all right, and you'll be fine. Moving on. Okay, next over here, we have a wiring. I'll say the easiest way to approach this question, right, is to think about it this way. Do you ignore the 2? Yeah, the voltage is not relevant. It's always kilowatt per hour, so kWh. Now, the most important one is recognize that the one connected to the metal casing, what wire is this? Earth wire. right? So you know that this is the earth wire. What's the voltage of the earth wire? The voltage of the earth wire will always be 0. Question, if I have my fuse here, live wire or neutral wire? Live wire. And live wire is always at high voltage. Your neutral wire, on the other hand, I already passed all my voltage to the heater already. On the way back, is there current? Yes, right? Because there's charges flowing through back home. But what is my voltage? It will be 0 volt, right? So what's my answer? Answer here should be 8. So only the live wire is at high voltage. Both the live and neutral wire have current. I give you all 30 seconds to read through question 3 and let's talk about this. Okay, let's take a look at the screen, right? We connect to a 13 ampere fuse. When we switch it on, the fuse blows. Your instant conclusion is that the current right now is bigger than 13 ampere. Right? Otherwise, the fuse won't blow. The fuse only blows when it exceeds the fuse rating. Even if you fit it with a new fuse this time, it still happened again. Right? So the person decided to replace the fuse with a nail with negligible resistance. And suddenly the kettle works. Now, what's the implication? If you put in a nail with negligible resistance, if resistance drop, what happens to your current? Your current increases. In the past, the fuse was there to protect the appliance by melting. Break open the circuit, right? My device doesn't spoil. The large current cannot go through. Instead of putting a fuse, I put a metal nail instead. I allow the current to flow through. This extremely large current flows through. What will happen to your appliance? The very large current will overload the wiring, potentially causing a fire. A fuse is a good guy. He's not a bad guy. He's a safety guy. He tells you when it's too dangerous to continue. So just because the fuse melt doesn't mean I keep replacing it until it works. No, it's signaling to you that something is wrong, that the current is too big in the first place. So if you replace it with an iron nail and you say, oh, just go ahead, please proceed, gone, no? The whole thing will just overheat and burst. All right. So if a fuse melt is telling you that something is malfunctioning. Moving on. We're going to finish up the last 2 MCQ. All right. So which of the following situation would a fuse melt? This question, if you want, put an asterisk. I think it's very important. The answer is B. I'm going to tell you here and now that there are exactly 2 scenarios that will cause a fuse to melt. Fuse will melt when, number 1, short circuit. Elaborate. Short circuit means that I bypass my component. My current has found a shortcut whereby it doesn't have to pass through the component anymore. And because the resistance drop, current greatly increases. So in other words, the moment you hear short circuit, gone. Fuse will melt. Because the short circuit means resistance drop, current increases. The second scenario where your fuse will melt is when your earth wire is activated. Activated is just my own way of saying it. Meaning if the live wire touches the metal casing and the earth wire comes into play, where current flows through the earth wire's resistance is very small. So the current greatly increases, the fuse will melt. So what is important is not knowing how the fuse works. Everybody knows when current is too big, the fuse will melt. But it's more important to know the 2 scenarios that will lead to your fuse melting. And among the 3 options, there's only one, which is short circuit. Option 3, right, is more of a case of, hey, option 3, this is dangerous. But it doesn't cause a fuse to melt, right? Because we know that the fuse is supposed to be on the live wire. But if you put it on the neutral, would it melt immediately? No lah. It will melt when the current is too big. But it no longer serves the purpose of isolating the appliance from high voltage. Okay, so you need to understand the difference between dangerous versus causing the fuse to melt. And lastly, question 5. By right, this is your earth wire. Your earth wire is supposed to be connected to the top of the 3-pin plug. So what happens when the plug is used? The earth wire now is connected to the live terminal instead. So what's the implication? Answer is B. Why? Because your earth wire is always connected to your metal casing. So if you plug it in, now your earth is connected to the metal casing and your earth now is at high voltage. Your metal casing would be at high voltage as well. Means if you touch it, you get electrocuted. So you make sure, I don't think you unplug every 3-pin plug to check lah, but if some electrician wire it wrongly, is GG lah. Okay, so just understand the function of the earth wire and why it needs to be there in the first place. Okay, as we have predicted, we talked about how likely we'll run out of time, which is why in the first place, when we prepared the materials, we prepared the answer key. I was quite certain we won't go through magnetism, but I'm glad we managed to spend a lot of time on the 3 major topics from current, a lot of time in DC circuits, but well worth it, and finally in practical electricity. So I hope today you had a better understanding and a good practice on what are the questions to come for it, and all the best for your WA2. But before you go on, we have some stuff we want to give to you for free, but we only got one request. Can you help me do a feedback form? Can? Okay, reasonable request, right? Okay, so just help me complete a feedback form. Really, the understanding here is how can we make the next revision better? So I believe it is this form, but wait, let me double check. This either brings me to the worksheet or the feedback form. I think this is the feedback form. Okay, it's a 1 minute, 2 minute feedback form. Can you just help me fill it up? Okay, then those that complete the feedback form, can you just show me the response submitted? We actually give you a free periodic table with all of the whatever trends inside. I just didn't periodic table, so you might use it. Just help me complete the feedback form, thanks. For those that are online, can I also request, do me a favor, help me complete this feedback form, especially if you enjoyed today's class. You can rate me very well, I'll be very happy. But if you think I suck, you can rate me poorly as well. We want honest feedback. Okay, but most importantly, I hope you had a productive night. Thanks for taking your Monday night and spending it with me doing physics. But hopefully you're a bit more well prepared for your WA. So anybody that wants the periodic table, show me your response completed, and then I'll pass you one. You need a prepared one. Yes. Anybody wants? Yes, thanks. They got food. They got how many do they call don't give your honesty, but just help me complete. Do they want the hand up? Yeah. Oh, anybody else needs? You just let me know. Yes, thanks. 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 The feedback will really help us. Thanks. So besides the periodic table at the side, you write the trend, bonding, all your formulas for your whole concept as well. So you'll be fine. Okay. Other than that, those of you with questions, you can stay back to ask me. Otherwise, that's all. Please go ahead to sign up for the remaining subjects if you want. Okay. No need to attend the physics one again because it's the same thing. But we're not going to stop you if you want to attend this. Thank you. Okay, for those online, thank you so much for joining. I hope you guys had a good night. I am Daryl, Elisa Daryl. Jadrian, if you really want to, you can drop by any of the branches to collect the periodic table or have your friend collect it for you. Very simple. Okay, but I hope all of you had a good time. This is Mr. Daryl, if you all need to complete your form. But thanks a lot for attending. All right. Please go and join the other subjects as well. I will leave the feedback form here for those that are still completing. Bye bye.